Here again is our simple two-link planar robot. And what we're going to do now is to consider the end effector velocity as a function of a very specific set of joint velocities. And that's the set of joint velocities that have got a magnitude of 1. We can think about this geometrically. What we're interested in is the set of all velocities that lie on this red circle. And here is a general point Q that lies on that circle. Points here and here correspond to motion of joint 1 only, and points here and here correspond to motion of joint 2 only. All the other points on the circle correspond to a mixture of motion of joint 1 and of joint 2. Another way we can write this constraint that the velocity lies on the red circle is in terms of this vector-vector product. It's the same as the dot product, saying the dot product of Q dot with itself is equal to 1. We have an expression for Q dot in terms of the Jacobian matrix inverse and the velocity of the robot end effector. So I can substitute this expression for Q dot into the above, and I get a complex expression that looks like this. What does that mean? Well, this is the equation for an ellipse, and it's ellipse in the velocity space. So in the coordinate system x dot and y dot, what we have here is an expression for an ellipse. So this is a particular velocity on that ellipse, x dot and y dot. So what's happened is we've mapped a set of velocities in the joint space, which was a circle, into a set of velocities in the end effector velocity space, and that is an ellipse. What this says is that the robot is able to achieve quite a high speed in the y direction, but a relatively low speed in the x direction. So it can go fast in the y direction and more slowly in the x direction. Now this ellipse that I've drawn is a function of the joint angle configuration. The shape of the ellipse depends on the way the robot joint angles are configured. Let's have a look at an example to get the intuition behind this. Once again, this is our two-link robot, and if I move joint 1, then the end of link 1 will move with a velocity like this. And if I move joint 2, then the end of link 2 will move with a velocity like this. The end effector velocity is the vector sum of these two velocities, so we can add the two vectors together, and this is the resultant. And what we see that in this particular configuration, the robot is able to move more quickly in the vertical direction than it can do in the horizontal direction. So for equal joint velocities, we will in general get uneven velocity in the different Cartesian directions. This depends on the robot's configuration. Let's have a look at how the robot's velocity ellipse changes shape as the robot's configuration changes. I've imported a model of the two-link planar manipulator, I've plotted it, and I've created a teach window here so we can see the blue panel at the side has got a couple of sliders that allow me to change the joint angles of the robot. And this is a plan view, a top-down view of the robot manipulator. So first thing I'm going to do is to adjust the joint 1 slider a little bit, and here we can see the robot's velocity ellipse, and it's very skinny indeed, and that's because the robot is at a near singular condition. So we see that in a configuration like this, the robot is able to move quite quickly towards the left and the right, but it's almost completely unable to move either upwards or downwards. Now, the configuration here is close to the singularity, and the singularity came about when the second joint angle was very close to 0. So let me increase the second joint angle, and what's going to happen now is that the ellipse gets wider and wider. The robot is further away from the singularity and is now in a configuration of joint angles that allows it to move quite readily along the direction of link 2 or orthogonal to link 2. Now if I reduce the second joint angle Q2, make it closer to 0, we see that the ellipse is going to get skinnier and skinnier, and ultimately it will become an ellipse of 0 width, a straight line